Hello student, I am Dr.A.K. Sinha, Professor of Chemistry. Today I am going to discuss packing third layer over the second layer. Already I have finished placing second layer over the first layer. Actually, just the main things I am telling you first before going to this placing third layer over the second layer. What I have discussed last class, that is the close packed structure. Close packed structure I have discussed. Under that I have discussed close packing in one dimension and close packing in two dimension. And third I have discussed close packing in third dimension. One dimension, two dimension and three dimension. One dimension means just length, no breadth. Okay. And second dimension means length and breadth both. And third dimension means length, breadth and height. All three is considered. Then in one dimension, all layers are touching to each other. All are touching to each other. Suppose 5 spheres are there. All are touching to each other. Okay, in one row. And in second, that in second dimension, that length and breadth also is there. Means suppose 5 sphere was there. Here sphere means atom or molecules or ions. Then in one dimension, all you can say spheres are just in one row. They are touching like that arrangement you have done. Second, that breadth was also there. Means other also 5. Suppose another layer was also there. 5. They are touching. Third also only in the ground, not one above the other. Only in one layer only. First row, second row, third row. Then length also is there, breadth also is there. That is called second, two-dimensional. Okay, because length and breadth both way you have arranged. And only in that you have seen in second, in second you can say in two dimension I'm talking about. In two dimension, two category was there. One was a square close packing. A square close packing means in the middle, any sphere in the middle you will see, then surrounding this 4 layer was arranged. 4 sphere was arranged, and in the middle 1 sphere was there. Okay, in the middle 1 sphere and it is surrounded by 4. That is called a square close packing. And other case was there, that surrounding one 6 sphere was arranged. That is called hexagonal close packing. Okay, then a square close packing, it is arising when you can say a arrangement you will do. In same type of arrangement you will do. Suppose 5, 6 sphere was there. Then above that another you can say or you can say touching to this first row, second row also you have arranged same way. Third layer also, third row you can tell, third row, fourth row, all are touching, all are adjacent. Okay, then in the middle gap you got them in the middle gap. That is called A type. A first row, again second row A type arrangement, third also row A type, fourth also same way, just in adjacent, all rows are there in adjacent, all are touching to each other. Then in that way you will get a square close packing, because in the middle one and surrounding this 4 are there. And in second case, that you have second row you have arranged in such a way that second row it is coming void in the middle of two sphere. Next row you have put in the gap. In the gap you have started keeping the other spheres. Correct? Then here A is one type, B is another type. Because B you have started arranging between the gap. You started arranging between the gaps. Then here also all are touching. Second row all spheres are touching, but you have started with gap. You are keeping in the gap. That's why here you will get hexagonal, means any sphere in the middle you will see, then you will find that this surrounding the middle 6 layers are there, 6 spheres are there. Suppose you have arranged A type, B type, again A type, again B type, means A arrangement is same, but B is differing, that is started from the void. Started from the void means gap. Then A type, then B type, then again A type, then again B type, means AB type. Then here you will get that middle or center sphere is surrounded by 6 sphere, hence it is called hexagonal close packing. Then now the third is the three-dimensional. Okay. Then close packing in three-dimensional. Then here you have arranged height also, means 2 dimension was there, length and breadth. Now above this layer, first layer, second layer you have put, second layer, third layer, fourth layer. Suppose 5 into 5. First layer 5 into 5. Second layer again 5 into 5. Third layer again 5 into 5. The fourth layer also 5 into 5. Then here again you will find that height now also increased. Length, breadth and height, it became three-dimensional close packing. Then here you will see any in the middle, then you will find that in the center, from the any one side, from the any one face you will see, then you will find that between the 4 sphere in the middle one gap is there. In the middle one gap is there. It will form just like a cube structure. It will form like a cube structure. Hence this is called simple cube lattice structure. Simple cube lattice, you can say structure, AAA type arrangement. AAA type. Okay, everywhere you will find same type of structure. Gap in the middle between the 4, one gap you will see. Then this is the three-dimensional structure. Then here already I have discussed in the last class. Now new things I am going to discuss. This is actually here I told you, in this also in three-dimensional 2 cases are there. In three-dimensional close packing structure there are 2 types. First is that three-dimensional close packing from 2-dimensional square close packed layer. A square close packed layer, you are getting one square, just now I told. Second, 3-dimensional close packing. This is also 3-dimensional because 2 types are there. Then second is 3-dimensional close packing from two-dimensional. But here you will get hexagonal closed packed layer. Hexagonal means now here you will see that central anywhere you will see any face, you will find that central atom is surrounded by 6. But only thing is that it is in 3 dimension. In the second dimension also you have seen these two cases. These two cases you have seen in the 2 dimension. Only in the you can say length, breadth was there, height was not there. But if you will consider 3 dimensional, then again you will find these two. Means a square like that cube you are telling, and other that hexagonal. Hexagonal means this in the middle center, one white below there, that is surrounded by 6 sphere. That is called hexagonal packed. Now this I am going to discuss new things here. You can say this packing third layer. Now on the second layer here in 3 dimensional. In 3 dimensional, now I have told you that 2 cases I have discussed. Okay, 2 cases I told you. First 3 dimensional closed packing from 2 dimensional square closed packed layers, and second I told you 3 dimensional closed packing from 2 dimensional hexagonal closed packed layer. Only in that third is also there. Okay. Then here in second you can tell second case. In second case actually there are 3 cases. In second cases means case of hexagonal. In case of hexagonal there are 3 cases. First is that packing second layer over the first layer. Actually one layer is there, and above that another layer is there. Then this is called actually packing second layer over the first layer. Okay, one case. Like that way, second is there, that is the packing packing a second layer over the first layer. That is the first case. And second case is that packing third layer over the second layer. This is the second case. Packing third layer over the second layer. First I told you packing second layer over the first layer. Now here packing third layer over the second layer. I am going to discuss here. And here again there are 2 cases. Now actually what will happen, gap you are going to cover. Gaps are going to be covered. Here this is the main point. Placing third layer over the second layer, what will happen by this? Then here you will cover the voids. Gap is there, that are going to be covered. When third layer is placed over the second, there are 2 possibilities. It is I told you 2 types. When third layer is placed over the second layer, then there are 2 possibilities. First, covering tetrahedral voids. First is covering tetrahedral voids, and second is covering octahedral voids. Okay, covering tetrahedral, tetra means 4, hexagonal means 6. Now we are knowing. Then here, first covering tetrahedral voids. Here what will happen? Tetrahedral voids of the second layer may be covered by the spheres of the third layer. In this case, the spheres of the third layers are exactly aligned with those of the first layer. First layer and third layer is same arrangement. Middle is different, means A, B, A. Here arrangement will be A, B, A type pattern. A, B, A, again B. Like that way, A, B, A, B. This pattern will work. Then A, B, A means first and third, they will be exactly aligned. Same arrangement. Only between the two A, B, A. Then B will be different. Okay. This pattern is often written as A, B pattern. This structure is called hexagonal close packed structure, HCP. H means hexagonal, C means close, P means packed. Hexagonal close packed structure, A, B, like that way. Even 4 layers are there, A, then B, and then A again B, like that type of pattern. This is called hexagonal close packed structure. Here you can understand very well actually this type of arrangement. First to understand example, then I will tell you this in details. This sort of arrangement of atoms, so you are talking how atoms are arranged in any metal. In which metal this type of arrangement is there? In which metal crystal, this type of arrangement is there? In which metal? Then example is, you will find this sort of arrangement of atoms is found in many metals like magnesium and zinc. You will see the arrangement of magnesium, many atoms will be there. Then if you will see from the microscope arrangement, then this type of arrangement is there. A, B, hexagonal. Zinc also same type of structure you will find. Okay. Then here again easily you can understand that suppose 6 sphere you have taken, 6 sphere. Just to all sphere just to keep together, then obviously means to one side, to down, to left side, to right side. Correct? Left side to right side to, and direction wise you can understand better. North side to, south side to, east, west to. Correct? North side to, south to, east to, west to. All you make it, all should touch it, keep close. Then you will find in the middle gap is there. Then now above this means second layer, B type arrangement I am talking about. Now you keep 3 layer you keep. on this 6 sphere, above the 6 sphere, now 3 sphere you keep upside. On this 6 sphere you keep above this 3 sphere. Now again above second, third you keep, third layer, 6 you keep, 6 you arrange. You just to imagine only, just to imagine, because in metal many metals will be there, many in metal many atoms will be there, many atoms, then all will be touching each other, hence they will balance it. But here just only a special arrangement, one unit arrangement you are just considering. Then just to think 6 sphere down, above that 3, again above that 6, again above that 3. Like that type of arrangement you consider. Correct? Then this type of arrangement actually is called hexagonal close packed structure. HCP. It is called HCP, hexagonal close packed structure. And then here this you can separate also. Just imagine one layer, after that 3 layers separate you think, again above that 6 separate you consider, again above that third A B that you can imagine. Okay, and again that you keep it all together really. Then two types of diagram you will find. Okay, 2 times. One is separate, just imagination. Now really automatically all will touch if you will keep it. Then that is the second type. Like that way, if you can say 3 different arrangement is there. If 3 layers are there, then first layer is A type, other layer is B type, and third layer is different, C type. 3 type of arrangement. Now you think 3 layers are there, all layers are different arrangement. A type, B type, C type. Then here one thing you have to understand. Very easily you can understand. Example I am telling you. See, these things you have seen when you are math you are solving numericals, then that time since symbol you are writing 1 point above, 2 point down. Correct? 1 point above, 2 point down. That is you are writing since. Okay, 1 point, total 3 point, 1 point above, 2 point down. Now imagine reverse case, 2 point above, 1 point down. Then see 3, this you consider as a 3 sphere, 2 up, 1 down. And in second case, 1 up and 2 down, reverse case. Correct? 1 up, then 2 down, and 2 up, then 1 down. This 2 diagram you consider. Then now what I am going to discuss, it will be very easy to understand in a practical way. Only imagination little you have to do. Then here what you have to do, A, B, C, again A, B, C. Like that you can arrange. All 3 arrangement is layers are different. Then here now what you have to do, that first to take 6 sphere like first one what I told you, and above that now second layer you keep like that 2 cases I told you, since 2 cases, correct, and 2 up 1 down, other 1 up 2 down. Then here now you keep on the first layer 6 you have kept, above that 3 layer you keep, then first case that is 2 above 1 down, and third layer again 3 layer you have to keep, but 1 up and 2 down. That arrangement you have to keep. 6 down, after that 2 times 3, 3 are keeping. But only you have to do, in first case 2 up and then down 1 you have kept. And in third case, third layer arranging, then 1 up and 2 down. Correct? Then 3 arrangement we have done. First layer 6, second layer 3, third layer again 3. But arrangement we have differed. In one case, you can say 2 was above, 1 was down. Third case, 1 was above, 2 was down. That type of arrangement, like a triangle. 6 is down, first layer, then triangle, 1 point up, 2 point down. You have made it like that arrangement. Third, again 1 point down, 2 up. Then here point means a sphere. And fourth one is again like first one. Fourth one is just like first one arrangement. Means you can tell that now we have arranged A, B, C, again A. This type of pattern. A, B, C, again A, B, C. Like that type of pattern. Then this type of arrangement actually is found in magnesium or zinc, Zn, Mg or Zn. Then here also, first you imagine separate, and again you just touch it. That arrangement, that imagination you can do. Then here, in this case, again you will find 2 type of diagram. Correct? All are separate. 4 layers you have made, A, B, C, again A. Suppose. Then all are gap, suppose you are separate. Now, in second case, you touch it. Means really what happens. Then here again you will get 2 type of diagram. Okay. And then here I have told you first what I told you, hexagonal packed means HCP, hexagonal, you can say packed, and now second I told you closed, cubic closed, CCP. This is called CCP, cubic closed packing. CCP, cubic closed packing. And first case I told you hexagonal packing. Okay. Then now I am going to tell you this second type, covering octahedral voids. Now I discussed covering tetrahedral voids. In that I have given 2 examples, hexagonal packing and cubic closed packing. Now second case was covering octahedral voids. There tetrahedral voids covered. Now I am going to discuss covering octahedral voids. Means 6. You have seen that in the middle one gap is there, and surrounding that 6 spheres are there. Then now we are considering that things. Then here again you can understand very easily. The third layer, here also you are keeping third layer. Third layer means all are different. Third layer means here different arrangement, A, B, C. But here I will tell you what is the difference. The third layer may be placed above the second layer. Third layer may be placed above the second layer in a manner such that a sphere cover the octahedral voids. When placed in this manner, the spheres of the third layer are not aligned. Here not aligned. Keep in mind. When placed in this manner, the sphere of the third layer are not aligned with those of either of the first or the second layer, because A, B, C all are different arrangement. That's why they are not aligned. This arrangement is called C type. A, B you have seen. This is third type arrangement, that is called C type. Only when fourth layer is placed, the spheres are aligned with first one. Okay, when fourth layer you will keep, then first and fourth will be the same, but continuously A, B, C are different. A, B, C are different, but fourth one will repeat what I discussed earlier, like the A, B, C, A. Same way here, it will be there, A, B, C, A. Then now I am telling you, just by imagination, you can understand very easily. Okay. Here what here what you have to do, you take one sphere. You take one sphere, and above this sphere, actually you keep six sphere. Just imagination you do first. This first you have taken only one sphere, and above that six sphere you consider, and in the middle one gap will be there, obviously in the middle gap will be there. Then this first layer one sphere will cover you can say this gap. This void will be covered from the down, correct? Because upside you are considering six sphere, then down gap is covered by one sphere, correct? Down gap is covered by one sphere. Now means you can write like this, first you six layer, how will you arrange six layer? Then first you keep 3, then 2, and then 1. Okay, this 6 how will you keep? Then first 3, then 2, and then 1. This type of arrangement you have to do. Okay, means 3, 2, 1. That is the B type. A type is only one down, only one. Second B type, 3, 2, 1. This is a B type. Third type, that is the just reverse of second one arrangement. Reverse of second one arrangement means 1 you keep, then you 2 keep, then 3 you keep. Then 1, 2, 3. Total 6. Then this type of arrangement, just first you consider separate. One sphere, above that 6 sphere is there. The second layer is 3, 2, 1. And third layer is 1, 2, 3. 1, 2, 3. Correct? And fourth layer you consider just like first one sphere. Then one sphere, and the 2, and the second 3, 6. Second sphere 6. Third again 6. Only arrangement is different. Second layer 3, 2, 1 arrangement. And third layer 1, 2, 3 arrangement. Fourth layer again only one sphere you can arrange. Suppose all are separate. One layer, above that second layer, consider separate, gap is there. Suppose third layer again gap is there, fourth again gap is there. Now in second diagram, you think all are touching to each other. Really all are kept to each other. Correct? Then this actually it is called covering octahedral voids. Okay, this I have discussed. Okay, this I think you might have understood this structure. This is actually I told you there A, B, C, A structure. Okay, A, B, C arrangement of layers when octahedral void is covered. And again another I told you same way, that is called fragments of a structure formed by the arrangement of resulting in cubic closed packet, CCP structure. CCP structure is also called CCP structure is means C cubic closed packing, CCP is also called FCC structure, face centered cubic structure. Face centered. Face also you know that cube one part is there. Cube one part, one face, cube one face, and one center will be there. That's why a face centered cubic structure. Okay. Then this I have discussed about the covering octahedral voids. Okay. Then this I have discussed. Now this things cubic closed, already told you cubic closed packet CCP or FC, face centered cubic, FCC structure. Okay. Then metals such as copper and silver, where you will find this type of arrangement. This I told you covering 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 octahedral voids, covering octahedral voids. What is the example in which metal you will find this type of structure? Then its structure is copper and silver is the best example. Copper and silver crystallize in this structure. Example always you keep in mind. Okay, examination question is asked. Then this covering hexagonal void, its example is copper and silver. Copper and silver. And first one example was magnesium and zinc. Magnesium and zinc. Okay, this is very, very important. That was first one was I discussed that tetrahedral, placing third layer under the second layer. In that two cases I told you covering tetrahedral. Its example is magnesium and Zn. And here covering octahedral. Covering octahedral voids. Its example is copper and silver. Question is asked. Now other things I am going to discuss. That is the formula of a compound and a number of voids filled. Number of voids filled means first you have to find in any crystal. In any crystal, how many you can say voids are there. How many voids are there? Gap. Then formula of a compound. Formula of a compound and number of voids filled. When you are saying how many voids are there, only then you will fill it. Then this is the special topic, formula of a compound and number of voids filled. Then here I will give one two example, then you will understand this. Okay. We have already seen that when particles are close packed means touching to each other. Okay, always keep in mind. When particles are close packed, resulting in either CCP or HCP structure. When all will touch to each other, then it will result in either CCP or HCP structure. CCP now you know, C means cubic, C other C close, P means packing, CCP cubic close packing, or HCP means hexagonal close packing structure. If you can say particles will touch, then they can form this two type of structure. Two types of voids are generated. Already I have told you. While the number of octahedral voids while the number of octahedral voids present in a lattice is equal to the number of close packed particles. Here you have to understand. While the number of octahedral voids present in a lattice is equal to the number of close packed particles, means both particles, number of particles is equal to the voids, octahedral voids. Okay. The number of tetrahedral, here you have to understand, difference is there, you understand. The number of tetrahedral voids generated is twice the number of ionic, twice the number of tetrahedral voids generated is twice this number. Means what is the number in octahedral? Double of this. In tetrahedral it will be double. Octahedral and number of particles both are same. Octahedral voids and number of particles are same. But if suppose it is forming tetrahedral, then the number of tetrahedral voids generated is twice this number. Okay. Particles number twice of the particles number. This is very, very important things. That the number of tetrahedral voids generated is twice this number, means particles number. In ionic solids, example I am telling you that here in ionic solids, the bigger ions, in ionic solids, again important points are there. In ionic solids, the bigger ions, what will be the bigger ions in ionic solid? Which one is bigger, anion or cation? Anion. Because why anion will be bigger? Because it will take electron. It will take electron, negative charge, that is called negative charge. Anion, that's why new orbit may opened. Hence size will be big. And cation will be always smaller. Because suppose, as for example, sodium due to one electron, one new orbit is opened, 281. Then if this electron goes out, it gives, then only 2 orbit will be there. Then it will become, after losing the one electron, only 2 orbit is there. That's why size will be less. But this electron, if other atom will take, then it may new you can say orbit may open. Okay, then size will increase. Okay, then because number, or also you can just understand that number of electrons will increase in number in anion. That's why size will increase. Okay, then this I told you that anion will be bigger. In ionic solid, anion will be bigger, cation will be small. Okay, in ionic solid, the bigger ions, usually anion, form the close packed structure, and the smaller ion, usually cation, occupy the void. Because it is small, it can enter into the void. Because it is small, then because it is small, it can enter into the voids. Keep in mind. Okay, this is very, very important things. The bigger ions means anion form the close packed structure and the smaller ions occupy the voids. If the latter ion is a small means a cation. If the cation is small enough, then if it is very small, then tetrahedral voids are occupied. Okay, if cation's ion is small enough, then tetrahedral voids are occupied, will be filled, occupied. Okay, tetrahedral voids. And because this is a small, that's why number will be double. Number will be double. Tetrahedral voids are occupied. If bigger than octahedral voids, if suppose it is a smaller, I told you, if a smaller, then tetrahedral voids are occupied. If bigger, then what will happen? If cation is bigger. If bigger, then octahedral voids are occupied. If bigger, then octahedral voids are occupied. Means bigger will form octahedral, a smaller will form tetrahedral. Okay, this is question is asked. Okay, now in a given compound, the fraction of octahedral, how many octahedrals are there, how many tetrahedral voids are there? Two types of voids are there, octahedral voids or tetrahedral voids. Then in a given compound, the fraction of octahedral or tetrahedral voids that are occupied depends upon the chemical formula. Correct? How many octahedral voids are there? What is fraction? Fraction means always out of total ions, how many are octahedral? In that, how many are octahedral, how many are tetrahedral? Out of total, just like a percentage. Out of 100, 60 may be octahedral, 40 may be tetrahedral. This percentage, fraction. Yes, that is called fraction. 60, 40 like that, 30, 70 like that, 20, 80, 80, 20. Okay, just example I am telling you. This is called fraction. Then this in a given compound, the fraction of octahedral or tetrahedral voids that are occupied depends upon the chemical formula of the compound. Okay. Now I will give two examples, then you can understand. Okay, it is represented by chemical formula. Just like I am telling you example, NaCl. NaCl formula, that is XY, you can tell. This formula you can tell as XY. NaCl. And NaCl crystal you will see, you will find like this. All are arranged like that. Na, then Cl. Again Na, again Cl. Again Na, again Cl. Just like in cubic form, it is arranged. And also you might have seen formula like these things. H2 this any formula you can consider, as for example you can consider as a SO2, or you can say other formula, these things you can consider as a H2S, SO2, Na3P4, sodium phosphide, Na3P4, correct? Then Na3P4 means if sodium ions are 3, phosphorus is 4. In that case you will find Na3P4. Then as means cation is different, and phosphorus is different. Okay. Then this I have told you example, this type of compound also you have seen. Then how this formula comes? Then actually this formula is depending upon the number of cation and number of anion. Number of cation and number of anion. Okay. Na3P4 is the best example, sodium phosphide. Then now example I am telling you, in examination also they can ask a question on this basis. Then question I am first reading, then you can understand. A compound is formed, question I am reading. A compound is formed by two elements, X and Y, capital X and capital Y, just like NaCl you can consider, X and Y. Atoms of the element Y, consider as a anion, just like a Cl you can consider, Cl minus. Then atom of the element Y means here anion you can consider, makes CCP, and those of the element X means cation occupy all the octahedral voids. Means X and Y is there, then Y is making CCP and X is occupying octahedral voids. Okay. Y is means anion is a CCP means tetrahedral, and Y and X is Y is CCP means tetrahedral and X is octahedral voids. Then what is the formula of the compound? Question. This is the question. What is the formula of the given compound? Then its answer I am telling you, solution I am telling you. The CCP lattice means tetrahedral. The CCP lattice is formed by the element Y. The number of octahedral voids generated would be equal to the number of atoms of Y. That already told you. Okay. Tetrahedral will be double. Keep in mind, double. The number of octahedral voids generated would be equal to the number of atoms of Y present in it, means anion. Okay, it is bigger size. Then octahedral is due to the number of octahedral voids generated. That is according to the Y, number of Y. The number of octahedral voids generated would be equal to the number of atoms of Y present in it. And other things here, since all the octahedral voids are occupied by the atoms of X, that is clear because X is a small. Then obviously all the tetrahedral voids are occupied by the atoms of X. Their number would be also the equal to that of the element Y, because wherever this is there, wherever you can say Y is there, X will be there. Okay, since all the octahedral voids are occupied by the atoms of X, their number would also be the equal to that of elements Y. Both are same. X and Y will be the same. Thus, the atoms of elements X and Y are present in equal number or 1:1 ratio. Therefore, the formula of the compound is XY. XY because both numbers are same. Okay, number of octahedral voids is equal to number of tetrahedral CCP. That's why 1:1 ratio formula will be XY. Okay. Now, second example I am telling you. Atom of, a question I am reading, atoms of elements B form HCP, hexagonal, this HCP lattice. H means hexagonal, C means closed, P means packing, HCP. Atoms of elements B form B, capital B, form HCP lattice, and those of the element A occupy 2/3 of tetrahedral voids. 2/3. 2/3 means how much percentage? 66%. 66%. And rest 33%, roughly I am talking about, that will be A. 33 and 66. Okay, you can understand like that. Again question reading, atoms of elements B form HCP lattice and those of the element A occupy 2/3 of tetrahedral voids. What is the formula of the compound formed by the elements A and B? Formula. Then now here question you have understood that A occupy 2/3 of the tetrahedral voids. 2/3. And B forms HCP lattice. And now I am telling the answer, or you can tell solution. The number of tetrahedral voids, form is equal to twice the number of atoms of element B. Already I have discussed the tetrahedral number will be twice. The number of tetrahedral voids form is equal to twice the number of atoms of elements B, and only 2/3 of these are occupied. That is a double, that is clear. It will be octahedral will be double. But it's what is the value if it is okay, double will be there, that is as a principle. But it's a number they have given 2/3, like a 66%. But number is only 2/3 of these are occupied by the atoms of elements A, 2/3. The number, again I am telling you, the number of tetrahedral voids formed is equal to the twice of number of atoms of element B, number of atom B, and only 2/3 of these are occupied by the atoms of element A. Okay, 2/3 B I am talking about, that is a 2/3 atoms of elements B, and only 2/3 of these are occupied by the atoms of element A. 2/3 of these are occupied by the elements of A. Rest are by B. B means B is less, A is more. Hence the ratio of number of atoms of A and B is what is the ratio? Then ratio of number of atoms A and B is 2 into 2 by 2/3. 2 into, you are going to multiply by 2. 2/3 multiplied by 2. Okay. The ratio of the number of atoms of A and B is 2. 2 into 2/3. 2 is to 3rd is to 1. Because tetrahedral will be double. Then 2 into 2 by 3. Okay. Is to 1. Then that is, you can tell 4 by 3. 4 is to 3 you can tell. 2 into 2/3. 2 into 2 by 3. divided by 1, because ratio is like this only, A and B ratio, then A ratio is 2 into 2 by 3, that is the 4 by 3, that is the A, and B is only 1, B is only 1. Then A to B ratio is 2 into 2 by 3, means 4 by 3, divided by 1, okay. Then it will be 4:3 ratio, 4:3 ratio. Hence the formula of the compound, compound formula will be A4B3. A means A is 4, A is A4B3, means A is in 4 number, then B will be 3 number. A will be 4 number, B will be in 3 number. Okay, then this formula is A4B3. Now from the question, from the question, now again direct answer, you can understand that atoms of element B forms a HCP lattice, and those of the element A occupy 2/3 of tetrahedral voids. A occupy 2/3 of the tetrahedral voids. Correct? It means A occupy 2/3 of the tetrahedral voids. A. It means A is in more number. A number is more. 2/3 of the tetrahedral voids A occupy. Then it means A is more and B is less. B forms HCP. Then tetrahedral obviously will be more. Tetrahedral will be more and octahedral will be less. That's why B forms HCP, means octahedral. Octahedral number will be less. B question they are telling atoms of element B forms HCP, means octahedral. Octahedral will be less. Octahedral will be less and tetrahedral will be more. Then A occupy 2/3 of tetrahedral voids, means 66%. Only A is there, means A is more, B is less. That's why formula you got A4B3. A4B3, because 2/3, double of the 2/3. Double of 2/3 is A. Then like that way 4:3 ratio you got, and formula is AX A4B3. A4B3. And this I have discussed. Okay, next class again another things I will discuss. Thank you.